Okay, as we saw, the wave that we're analyzing will have something over 12 wavelengths between 0 and 6.7 meters. 6.7 meters, I thought I heard somebody say it was 12.06 wavelengths, not 12.6 as I originally had it. That would have been here. I've erased it. But I got 12.46. Wherever this is, it's going to be 12 full wavelengths, which is here, and then whatever this fraction is of another wavelength. Here would be half a wavelength, here would be a whole wavelength difference. The time delay from 0 to 6.7 centimeters is what? It's time delay of 6.7 meters divided by the propagation velocity of 50 meters per second, 0.134 seconds. So it takes 0.134 seconds for whatever's happening here to be repeated here at the 6.7 meter point. Now, so, said it again, at x equals 6.7 meters, the simple harmonic motion is the same as it was at x equals 0. And you can translate that statement as you wish. The point then being that the y displacement, the displacement perpendicular to the direction of propagation of the wave at time t at 6.7 meters is going to be 0.1 meters times the sine of not 180 pi t, but 180 pi times the quantity t minus 0.134 seconds. So, we could also got my parentheses in the wrong place here. I'm going to pause and fix that. Sorry, pause for no good reason. I thought I saw something wrong, but there wasn't anything. Here's what we have for 6.7 meters. Now, what's the time delay if we want to do an arbitrary position x on the x-axis? Okay, it's an arbitrary position. What's the time delay from here to an arbitrary x? Well, it should be clear by analogy with what we just did that the time delay is going to be the position to position x is going to be x divided by the speed of the wave, because x is how far it is from the left hand end, or from the x equals 0 position. If we divide that by c, which in this case is 50 meters per second, we get the time delay. And the time delay then, well, 1 over 50 is 0.02, there's our x, and it's going to be in units of seconds per meter, since we're dividing by meters per second. The units are going to invert. So we get y of tx equals 0.1 meter times the sine of 180 pi t times the quantity t minus the time delay, which is 0.02x seconds per meter. Now, the next thing we're going to do, well, let's talk about this for a second. This formula here, this equation, tells us the position of the y position of a point at any position x at any time t. So we plug in x, we plug in t, we see how far that particular point on the string is displaced from its equilibrium position. Now, this is an example of the equation of a wave. Now, there's also something called the wave equation, and we want to distinguish the two. We're going to verify that the equation of this wave satisfies the wave equation. Now, you don't know what the wave equation is yet, but I'm just going to ask you to do simple calculation, a couple of simple calculations. Taking the equation of the wave, the y of tx, we want to find the second partial derivative of y with respect to t, and the second partial of y with respect to x. And we're going to develop that into something that has a little meaning and that we can relate to what we call the wave equation.